Deep inside every single internal combustion engine, there's this constant battle going on. It's a fundamental conflict, really, between two totally opposite desires, that raw, unadulterated thirst for power and the sensible need for the best possible fuel economy. So today, we're going to dive into this performance paradox and the absolutely brilliant mechanical device that tried to solve it. Okay, to really get a handle on just how big this challenge is, think about this number, 5 milliseconds. At 6,000 RPM, that is the entire window of time an engine has to create the perfect combustible mixture of air and fuel. I mean, a camera flash, that lasts longer than that. It's an incredibly violent, incredibly precise, and unbelievably fast process. So this whole process of getting that mix just right, that's called carburation. It's really the art and science of blending fuel with air in the exact right proportions to get a clean, powerful explosion inside the cylinder. And if you get it wrong, well, you're looking at lousy performance, terrible efficiency, or, you guessed it, both.
So, what does an engine actually want? Well, this is where things get tricky. See, it doesn't just want one thing. It wants different things at different times. And a lot of the time, those wants are in direct opposition to each other.
And what's so fascinating about this chart is how clearly it lays out the problem. That top curve, that's power. The bottom one is fuel consumption. And you can see the peak for the absolute best power happens with what we call a rich mixture, about 12 parts air to 1 part fuel. But the point of best economy, where you're using the least amount of fuel, that happens with a much leaner mixture, around 16 to 1. And here's the kicker. Those two peaks, they don't line up, not even close. An engine simply cannot have its cake and eat it too. You can't get max power and max efficiency at the same time.
Okay, so knowing that, what would a perfect fuel system actually have to do? If we could wave a magic wand and design the ideal system, what would that performance curve even look like?
And here it is. This chart shows that ideal perfectly. You can see it's this kind of U-shaped curve. Way over on the left at idle, the engine needs a nice, rich mixture just to run smoothly. Then in the middle, when you're just cruising down the highway, it wants a really lean mixture to save every last drop of fuel. But then, you stomp on the gas, and all the way on the right, for full power, it's demanding a rich mixture all over again. Any fuel system worth its salt has to be able to hit all three of these zones.
Right, but why so rich at idle? I mean, that seems backward, doesn't it? Well, the problem is this weird phenomenon called exhaust gas dilution. When the engine's just ticking over, the throttle is almost completely shut. This creates a really strong vacuum, a super low pressure zone right in the intake manifold.
So let's break that down. First, that nearly closed throttle creates that intense low pressure. Second, this vacuum is actually so powerful it sucks leftover exhaust gases back out of the cylinder from the previous explosion. This old exhaust then poisons the fresh charge of fuel and air, watering it down. So to make sure there's enough good stuff in there to actually ignite, you have to add extra fuel, a richer mixture.
Okay, so here's the real takeaway, the huge difference between just cruising along and when you put your foot to the floor. When you're just driving normally, that exhaust dilution isn't a problem, so the system can lean out the mixture to that sweet spot, around 16 to 1, for maximum fuel economy. But when you ask for full power, the whole game changes. You need that rich 12 to 1 mixture, not just for the most bang, but also because that extra fuel that doesn't burn actually has a cooling effect, which helps protect the engine from melting itself under all that stress.
I mean, this is a seriously complicated set of demands, right? So how on earth did engineers solve this puzzle decades before we had microchips and sensors? Well, they created a mechanical masterpiece.
So let's meet our hero, the simple carburetor. You can think of it like a mechanical Maestro. It's this elegant, totally self-contained device that's designed to automatically sense how much air the engine is gulping down and then deliver just the right amount of fuel to match, all in an attempt to trace that perfect U-shaped curve we were just looking at.
So how does it work? Well, it all comes down to three main parts. The float chamber is kind of like the tank on the back of a toilet. It keeps a little reservoir of fuel ready to go at a constant level. The throttle valve is basically your gas pedal. It's just a plate that opens and closes to control how much mixture gets into the engine. And right in the middle, the real heart of the thing, the Venturi.
And the Venturi? This is just pure genius. It works on a really simple physics principle. As air gets squeezed through this narrow throat, it has to speed up. Think of a river flowing through a narrow canyon. And as that air speeds up, its pressure drops, a lot. This pressure drop creates a vacuum that's strong enough to literally suck fuel out of a tiny nozzle and spray it into the airflow.
The more air that rushes through, the faster it goes, the bigger the suction, and the more fuel it pulls in. It's just beautiful in its simplicity.
So you've got this elegant, totally automatic solution, no electronics needed. It seems perfect, right? But does it actually deliver that perfect U-shaped curve we're looking for?
Yeah. Well, here's where our story takes a little twist. Because for all its brilliance, the simple carburetor has a fundamental, completely unavoidable flaw.
So check this out. When we put the carburetor's actual performance, that's the dashed line, on top of our ideal curve, you can see right away they just don't match. Down at low speed, it's actually too lean to give a smooth idle. And what's worse, as the airflow increases into that cruising range where we want that lean mixture for good economy, the carburetor does the exact opposite of what we want. It just keeps getting richer and richer.
And that, right there, is the fundamental problem. The device's natural, built-in tendency is to add more and more fuel relative to the air as you go faster. Now that's great for making power, but it's terrible for fuel economy when you're just cruising. But why? How can this brilliant device have such a massive, built-in flaw?
You might think it's just bad engineering, but the answer isn't that simple. It's actually buried deep in the laws of physics, and it's what defines the carburetor's really elegant but ultimately imperfect legacy.
Okay, so the reason for this flaw, it all comes down to a tale of two very different fluids. You see, the carburetor is trying to measure out two things that behave completely differently. Air is a compressible gas. When it speeds up and its pressure drops in the Venturi, its density also changes. But fuel is an incompressible liquid. Its density stays the same no matter what. And this fundamental mismatch is the root of the entire problem.
Now, without getting bogged down in the math, this equation tells us exactly where the problem is. The final air-to-fuel ratio is directly connected to the square root of the density ratio between the air and the fuel. But since the air's density is always changing with speed and the fuel's density isn't, this ratio is a constantly moving target. It is, like the slide says, an uncontrollable variable. There was just no way for engineers to design around it. It's baked right into the physics.
So really, we shouldn't look at the carburetor as a failure at all. We should see it for what it was, an amazing mechanical computer. It was using the laws of fluid dynamics to come up with a pretty good approximation to an incredibly difficult problem. And in the end, it was those very limitations, its inability to perfectly trace that ideal curve, that pushed engineers to find a better way, which eventually led us to the modern electronic fuel injection systems that we all have in our cars today. And that kind of brings us full circle, you know? The simple carburetor might be a relic from another era, but the problem it was trying so hard to solve is absolutely timeless. That fundamental conflict between power and economy, it's still there in every engine built today. The paradox remains, it's just the solutions that keep evolving.